Okay. I'm still waiting for them to turn on the heat in this room. It's ridiculous. I've been feeling the radiators in the hallways, and I just think they haven't turned it on yet. Well, good morning. So I guess we're into chapter 4 now. Chapter 4 is going to be the last chapter that's going to be on your term test, which is coming up. Pretty sure it's like October 11th. It's a Tuesday night, so hopefully you're available then to come in. 6 o'clock, goes 6 to 7:30. We'll actually start it at 6:10, so even if you walk in right at 6:09, you'll have same time as everybody to do it. And it's in the EX building, which is down on McCall Street, 255 McCall. And so if you do have a time conflict at that time, you should register for the alternate sitting. You should click on the Quirks page and try to get that sorted out. We have an alternate sitting happening right before it on the same exact day. Yeah, so you can see I kind of wanted to do a lot of trigonometry review today, stuff that should be pretty easy for a lot of you. Like you probably should have it in your memory banks, and if not, we're going to do a lot of practice so that it is. Should we do a learning catalytics question maybe? Let's see if this thing's working. It is. So a large, light beach ball is accelerating downwards on a windless day. So which way is that? A, north, B, east, C, south, D, west, or E? The net force makes an angle of 90 degrees with respect to all 4 of these directions. I'll let you ponder that. Maybe set a timer for 1 minute while you discuss. So technically this might be a 3D question. I promised you we'd only be in 2D, didn't I? Let's see what survey says. Going once, going twice. Let's stop, send the screen here. So it's split. The ball is either pulled south or it's pulled in some other mysterious direction, which is 90 degrees away from north, south, east, and west. So you can see sort of from that what my idea was. So what we're going to do, I guess, I don't think we're going to end up doing the wave today. We're on trig. So, but what I wanted you to do is use your arms, and we're going to wait. Which way is it actually north in this building, I wonder? It's going to be that way, right? So we're going to do pointing. We're going to do north, south. And then there's, so point with me, north, south. And then let's do west, east. West, east. And then let's do up, down. Up, down. So down being perpendicular to all those different directions, right? So let's do it again with Santa Claus, Mexico. And we'll do, BC, Newfoundland. BC, heaven, hell, right? Okay. All right. So, yeah. We don't define south to be down or something. Students ask me that a lot. Do you define north to be up? No, I don't define north is still that way, up's that way. So, okay. I guess if I were to hang a map on my wall, I would probably choose to hang it with the north up, but that is a historical convention. All right, so we're on vectors. So yeah, there's two kinds of physical quantities you hear me talking about, scalars and vectors. Sometimes I say speed is a scalar, or mass is a scalar, temperature is a scalar, just described by a number. So you just say 5. So scalars are lucky because you can plug them into your calculator, whereas vectors have size and direction. So you can't just type a vector directly into your calculator unless you have a super fancy calculator. So you're always going to, in 2 dimensions, you're always going to use 2 numbers to specify a vector, or two pieces of information. One would be the magnitude, and one would be the direction. Or you could just use the x component and the y component. Again, that's 2 things though, right? You can't get away from having 2 pieces of information to specify a vector. So, and examples of that are position, I guess, your xy coordinate or something, your velocity, that's a vector, acceleration's a vector, force is a vector. They come up a lot in this course. And so we're going to do, a lot of people were struggling with this DSM that was Module 4, Vectors and Trigonometry. So can I just go over quickly just a few of these that seem to be giving people the most hassle? But yeah, basic idea here is just that if this is a sub y, that's the y component. And if this distance here is a sub x, that's the x component. And I usually just write those as positive numbers. And then this is like the opposite, and this is the adjacent, and this is the hypotenuse. So hopefully you kind of know about SOHCAHTOA. You're asked to find a sub x, so I'm going to use cosine of theta is equal to the adjacent side divided by the hypotenuse, which is going to be ax. That's why I chose cosine, divided by the hypotenuse, which is just a. Hypotenuse is the magnitude. I guess the magnitude of a vector is equal to just a. I'm just mostly just showing you all the symbols I like to use, and then you can just solve this out. I guess, what are you going to do? You're going to multiply both sides by a. It's the kind of stuff that I'm sure you can almost do in your sleep by now. And then, so this becomes ax, that's what you solved for, and that's a times cosine theta. Okay. And that was one of the multiple choice answers there. Another one, I'm going to do 4 of them. Another one was vectors a and b have equal magnitudes but point in different directions. They're not opposite directions, actually, because opposite always means 180 degrees away from each other, but they're definitely, one's going plus x, one's going minus x. It says, what is true about the y component of vector a compared to the y component of vector b? So they're talking about this is a sub y, right there, and this is b sub y, right there. So I would just say they're equal in magnitude, and they're both pointing up, right? They're both positive. So it's a plus and a plus. A sub y is equal in magnitude and points in the same direction to b sub y. Sound okay? What else did we have? We had this one. This one is, you're imagining a resultant, and I guess we could sketch it off here. If I was to put a little, I don't know how we would do this. I think it's probably going to be somewhere around there. This would be R. Anyway, I'm not a very good drawer, but somewhere around there. The point being that any time you have a vector that's like this, here's R, it's going to have some components. And it's a right angle triangle. So there's Rx, there's Ry, and there's r is like the hypotenuse. So this is Pythagoras, that you always have this. Square root of rx squared plus ry squared. This is the magnitude of. So it's a good equation to kind of have handy on your aid sheet or in your memory banks. Vector, okay. And what's interesting to note is that maybe I did have it straight up. It's hard to tell from this diagram, but note that if r sub x is equal to 0, then you would have that r is equal to the square root of rx squared plus ry squared. If rx is 0, then it's the square root of ry squared. Square root of ry squared. So it's the absolute value of ry or something. Anyway, the magnitude is, even if ry is negative or positive, the magnitude is just going to be the magnitude of ry in that case. Okay. And last one I'll do from these DSMs, there was this one just asking you to figure out r sub x, I guess. So it's long-winded, find r sub x. So in this case, what I would do is add the r sub x is going to be a sub x plus b sub x, right? That's the really nice thing about components, is that especially if you make them plus or minus, you can just add them up in your calculator, and it's the easiest way to really add vectors like this. Rather than doing head to tail and tip to toe or parallelogram rule or something, just add the components. And similarly, if they had asked you for r sub y, it would be a sub y plus b sub y. So all we have to do for this one is find the x components. So a sub x is negative 12.0 meters, because it's going in the minus x direction. And this one we're going to have to find. Here's b sub x, I think. Here's b is 18, and they give you the 37. So I would say that using my trig rules, b sub x is 18 times cosine of 37 degrees. So when I plugged that into my calculator, I got plus 14.38. And you should try this. Make sure your calculator is set to degrees mode. So on October 11th, you're not allowed to look at your telephone. So don't get used to using calculator mode on your phone for these kinds of things, because you won't have your phone during your midterm. But you get a calculator. So go and buy a $20 Casio or something like that and practice doing things like this. You should get 14.38. Make sure your calculator is set to deg mode as opposed to rad mode. If you use rad, which is a different unit of angular measurement, it's called the radian, you'll get it wrong. 37 degrees, right? Now what? Now I do r sub x is equal to a sub x plus b sub x. It's negative 12.0 plus 14.38. Now I'm getting a little confused about the significant digits here. I think what I would do is say, well, certainly it's 2.38. But if I was to do it by columns, 14.38 minus 12.0, I might want to round, because we didn't specify the hundredths column here, so I would say maybe 2.4 meters. Something like that. And don't forget the meters on both of them, I guess. Yeah. That was my last one there. I don't know why it said 2.40, because that's not correct. Okay. So those are the DSMs. These come up in forces quite a lot. This is an actual 5 Newton force. You can, split it up and say that F sub y here is going to be 5 times sine of 37. So it's plus 3 newtons, and that's your F sub y. This is your Fx. What I usually do is I just draw an Fx on there, and you figure out that that's minus. So I would say that Fx is just negative of the 5, and this time becomes the cosine, 37. Let's not forget degrees, so I get negative 4 newtons. And those are going to be really, really helpful if we're going to solve for acceleration or something, or compute the net force. Find anytime you have a diagonal force, you should split it up into its components so that you can add components to all the forces that are on your force diagram. Sometimes they give you the components and then you find the actual vector. Let's look at this one. Corinne pushes on a tree in the north direction with a force of 36 newtons. So I'm going to draw like the map view or something. So never eat shredded wheat, or whatever it is, or never enter stinky washrooms, or some way of memorizing that. And then, so there's your 36 newtons north. Daniel pushes on the same tree east with a force of 41 newtons. What is the magnitude of the net horizontal force on the tree? So these are both horizontal forces. You're looking sort of bird's eye view on the tree. So we can define, I guess, plus y to be north and plus x to be east. I'll put little plus signs on there. Anyway, it's just going to look like this. 36 is the north component, or the x component, fy, 41 is the x component, fx is 41, and this is f. So we're just going to use that f is equal to the square root of fx squared plus fy squared. So f is a pretty simple one. 36 squared plus 41 squared. Sorry if this is looking like a lot of review for you guys, but I think it's really important. We have these fundamentals that you can do these kinds of trig things quite quickly and reliably. So what's the point? The point is usually that we're finding acceleration. So often you're given a situation where you're told about some, maybe it's not a tree, maybe it's a cart, and one person is pushing on it north and one person is pushing on it east. If it's on a frictionless surface, you might be asked, what's its acceleration? You have to use the mass then of the cart. So Newton's second law, let me go to the next screen here. It's this. It's A is equal to the sum of all the forces divided by m. So that's a vector equation. The A is a vector, and the sum of all the forces is a vector, and the mass is a scalar. So what's a vector equation? It's a short form for two equations. So which are scalars. This represents two equations. So two equations must be true. And they are this, that A sub x is equal to the sum of all the forces in the x direction divided by the mass, and A sub y is equal to the sum of all the forces in the y direction divided by m. So it's like a short form. When you write the little arrow on top, what you mean is that is these two equations. The x component of the acceleration is the net x force divided by mass, and the y component of the acceleration is the net y force divided by mass. And these are really, and it's just written out the same way, or written out a different way. What's L though? Now I'm getting confused. I have no idea where I got this one from. Does anybody know what the L is? idea. But you get it. You're adding up all the forces that you've got. They're all on some S, and you're splitting them into components. And then ms is the mass of the object. S is here your object. I must have got this from the textbook somewhere. I don't know what the L was. Let's do an actual example. An object of mass 1.02 kilogram hangs on a rope, R2. There's another rope pulling it at an angle of 25 degrees to the left of down. So that's the upward rope, and this is the downward rope. And what is the acceleration of the object? So it's going to start swinging or accelerating. I've already drawn a nice force diagram there for you as part of the problem. I'm going to define plus y is up. Times up. Doing great. Let's define plus x is to the right. I think that'll be fine. So x here is horizontal and y is vertical. So now on this diagram we should put a gravity, which is what that is, Fe on Earth. So I'll just assume, I guess, no other forces on the object than the ones that are drawn. There's your force diagram. It's already drawn. Let's find components. We'll call this one, there's so many subscripts. Let's just call this one F1 and this one F2, because we're getting tired of all the subscripts. So let's find components. Theta is equal to 25 degrees. Let's draw F1 is that down one, and here's your theta. So this is, it's a negative F1y, and there's a right angle, and this is a negative, ran out of room here, but negative F1x. So that's supposed to be right angle, meaning that F1 sub x is equal to negative, 30 newtons times sine of 25 degrees, and F1y is equal to negative 30 times cosine of 25 degrees. And then the other thing I think we need, I guess we don't need anything. That's the only one that's diagonal, right? So now we can just say the sum of all the forces in the x direction is equal to, well, there's only one, F1x. It's just negative 30 times sine of 25. Because there's only one force out of the three of them that has a horizontal component, 25 degrees. And the sum of forces in the y direction, now anything that's going up is a plus, anything going down is a minus. So I'm going to say an F2 minus, let's call this one Fg because it's gravity, Fg, plus, well, F1y. We're going to, maybe I'll call it minus that. Minus the absolute value of that, right? Minus the F1y. It's a little confusing because I made it negative because I wanted to go negative, but you get me? It's going to be 40 minus mg, whatever mg is, and then minus 30 cosine of 25. And I think that 1.02 times 9.8 is equal to 10 newtons. So I get, well anyway, I can solve out for a sub x is equal to negative 30 sine 25 divided by 1.02. And a sub y is equal to 40 minus 10 minus 30 sine 25 all divided by 1.02. So a sub x is equal to, I got negative 12.43 meters per second squared. And a sub y, I got plus 2.756 meters per second squared. So when I plugged in all those numbers, I got that. So that's the components. I guess you could leave it at that if you wanted to. That does specify the answer. It says, what is the acceleration? But maybe you're asked for the magnitude. So the magnitude is a is equal to square root of a squared plus ax squared, ay squared plus ax squared. I think that's going to be 12.73 meters per second squared. And then the direction, if you know this one, but you can write it out here. You have to actually draw it. There's A, and it's in the plus y direction, and it's in the negative x direction. So we could maybe try to find this angle theta, where this is this is negative ax, and this is a sub y. So if you wanted to do that, you could use tan, which is opposite over adjacent. So you'd say that theta is tan to the minus 1, which is another button on your calculator that's good to find, of negative ax divided by a sub y. This is just if somebody asked you what the angle was, I guess. You could use this. So again, find the tan minus 1 button. You get 12.43 divided by 2.756. And I found in my calculator it was 78 degrees. Whoop. Sort of as defined in that diagram. So this is another way of specifying as magnitude and direction. Yep, question? Is the AY, oh yeah, sine, it's cos 25, isn't it? That's right, good point. So I think you're talking about this one up here. Yeah. Sorry, that should have said cos. Thank you. Again, I need a bigger chalkboard or something, although this is probably pretty big. Okay, let's do a learning catalytics question. Hit deliver. Okay, so this one is another one where you've got a vertical direction. Up is y, and now sideways to the right is x. So a string is attached to the rearview mirror of a car. A ball is hanging on the other end of the string, and the car is accelerating to the left in this diagram. So just from this list, which gives all the forces acting directly on the ball. So these are forces that you would put on a force diagram, for example. And I think I'll also put here that, a little assumption, assume that the windows are rolled up on the car, so there's not very much wind in the car. Which of course begs the question then, why is it at an angle? But we'll talk about that. Give you a minute to think about it, pair up, and then share. Think, pair, share. How many forces do we draw? And maybe we'll actually, I think if you know the angle, you can find the acceleration of the car. So maybe we'll do that for extra fun here. But first, let's finish this up. Going once, going twice. And survey says, it was like Family Feud or something. Survey says, bing, C, 65%. Okay. So the question is all this fictitious force to the right. So I agree, I guess, that in some, if you're doing your calculations in the reference frame of the car, maybe you should put a fictitious force to the right. But it is the custom of this course not to do that. We're not going to do that. We're going to imagine that we are in the frame of the road, the earth. I call this the lab frame, the unaccelerated frame. We had a whole philosophical argument about whether or not the earth is an inertial frame, because isn't it like rotating and orbiting the sun and all that stuff? But I think what we arrived at is that it's an approximately inertial frame. It certainly feels in Convocation Hall to be pretty inertial, right? And so there are small accelerations that are very steady due to the motion of the earth, but we're neglecting all that. So in the accelerating frame, what's going on is it's accelerating towards the left. So that's the acceleration of the ball, I guess. So what you do is you just draw the force diagram of the ball, force diagram of ball. You've got the tension acting up this way, tension, and you've got the normal force, or sorry, not normal, the gravity force acting down that way, and that's it. And so I think what these are going to do is they're going to add up. I don't know if you add them tip to tail or something like that. So that this will be the sum of the forces F net. Does that make sense? That's going to be directly towards the left, and that's why it's going to accelerate to the left. You don't need anything else. The whole reason it's tilted like that is so that when you add the tension plus the gravity, you get a net force which is directly to the left. That gives the ball its acceleration. Sound good? It's a bit tricky. It's all vectors. Do you want to do it just for fun? I like doing these problems. So let's take it a little farther. A string is attached to the rearview mirror of a car, and let's say that we've measured this angle, theta. So let's again go back to this force diagram, and now we'll drop components for everything. So, and what I'm going to do, just to make it even easier, is I'm going to define y to be up and x to be to the left. I know this is t sub x, and this is t sub y. Maybe it's not customary, but since it's accelerating to the left, that way we'll get a positive acceleration. So it says, what is the acceleration of the car? Okay, don't forget, so that's t. Don't forget also there's this one, mg acting downwards. So again, we just have to find what are all the net forces, right? So let's say that the forces in the x direction is just going to be tx, I think, which is going to be the tension times sine of theta. So I don't know if you believe me, but if the rope is going back like that, and this is theta, I used some sort of x rule to give that theta is on this top diagram. And the sum of the forces in the y direction is equal to, which should be 0 since it's not accelerating up or down. Okay, a sub y is 0. So f's y 0. It's going to be ty minus mg. It's going to be t cosine of theta minus mg. So from that I can get that t equals mg divided by cos theta. I can solve for tension, and then I can say that a sub x is equal to the forces, sum of the forces in the x direction divided by the mass. So it's equal to a sub x is t sine theta divided by mass. I can take the y component to solve for tension and eliminate it, by plugging it in to this equation and put it right in there. Make sense? So I get equals, I should say equals, mg over cos theta times, that's t, times sine theta divided by m. And then you look, the m's cancel. Doesn't even matter how massive the ball is to give you an angle. All that matters, so a sub x is the acceleration, is equal to g times sine theta divided by cos theta. So if you give me the theta, if you measure the theta, you can find the acceleration of the car. So if you have fuzzy dice, that's like an accelerometer. It's just measure the angle. And get it. And then there's another fancy trig identity. Do you guys know that like sine theta divided by cos theta, it's equal to opposite over hypotenuse kind of times or divided by the adjacent over the hypotenuse. You guys know this? Oh, sorry, hypotenuses cancel. And not that adjacent. You get opposite over adjacent, which is tan theta. So that's a fun little thing to also know. So some people just write this as g tan theta. Okay. All right. So then there's pulleys. I think that's the last thing I'll talk about today. And then on Friday we'll talk about friction, if that's okay. So pulleys. Yeah, so there's a couple of rules with tension. We've talked about it before, but the tension in a taut string or rope is a positive scalar number. So, you know, sometimes a string is kind of loose, and sometimes it's stretched out to be taut. That's what I mean by taut, is that I can twang it or something like that. If we can neglect the mass of the string compared to the other objects in the problem, then we say that you don't have to accelerate the string, right? So if the string is an object and it's pulling on a cart, the cart will pull the equal and opposite direction on the string. And if there's a mass hanging over here, which is the problem we're going to do, maybe I'll do a smaller, this will be the mass to hold you in place, and this will be the mass that I will hang. And of course, people on the video can't see me unless I press, there we go. Pius is all over it. So I've got a situation where I've got, it wants to move. You stop, you. Okay, so this is pulling to the left on the string, and this mass is pulling downwards on the string, and that is what is giving the string its tension. And if you neglect the mass of the string, then it can accelerate without any net force on it. So we just say the tension here is equal to the tension down here. And the other thing that we do in these problems is we usually neglect the mass of the pulley and also say it's a frictionless pulley so that even the tension on this side of the string is equal to the tension on this side of the string. So that's what strings do, is they sort of give tension, which as long as the string's massless and the pulley is massless and frictionless, the tension is the same on either side. So that's just one number you can write down for two force diagrams, which is you should do one for the hanging mass and one for the top mass. Can we go back to the slides? Thank you very much, because otherwise the asynchronous people will never see me. Okay, all right. If the string is wrapped over a frictionless pulley, we can neglect the mass, and we can neglect the mass of the pulley. Then the string has the same tension on both sides of the pulley. So let's do this one. This is the ye old mass on a frictionless table problem. We'll do it conceptually first. So you've got, it's very similar to the demonstration I just showed. I've got a frictionless table, something that can just slide back and forth, mass A. And I've got a hanging mass. So you want to ask yourself, first of all, is this system at rest? or is it accelerating at this moment? So this is I'll tell you, this is like a photograph, so you can't tell from just looking at it whether it's at rest or not. You have to think and make your decision, is this system accelerating or not, before you answer the question, okay? I'll give you a minute to think about that. Pair up and share. So I think the first step to this problem actually is looking just at A and asking yourself, if it's a frictionless surface, what are the forces on A? No friction. There's a tension force, right? And there's normal and there's gravity. So what are we going to say? Yeah, you have to remove the weight. So after I remove the weight, yeah, it's different. Should we, actually, why don't we do it? Can we, let's ox plate this thing. Not sure, just matters too much, but yeah, exactly. So it's different. It's when you do this. Okay. So it definitely is accelerating. So why is it accelerating? Because it's a frictionless surface and because there's a bunch of tension on A. Want to do it again? I've derailed. I hope you guys are taking care with your collision carts and practicals. I always advise every pod to set up someone who's a designated catcher at the end when you've got the fans going. It's going and so it doesn't just go flying right off into infinity. So maybe I'll be the catcher. Do you want to let it go, and I'll be the catcher? Thank you. Just so that doesn't happen again. 1, 2, 3, go. Okay. So it's definitely accelerating. A is accelerating. So going back to laptop 1. Thank you. So this is a dynamic situation with acceleration for sure. And now, since they're connected, I'm going to make the assumption that, like, if A moves 1 centimeter to the right, then B is going to move 1 centimeter down. Or if it's another way of putting that, if you do a derivative, if A is moving 1 centimeter per second to the right, then B will be moving 1 centimeter per second down, because they're connected. Or if there's an acceleration of A to the right, it's going to be the same as the acceleration of B down. That's the connected rule. So they have there's the same tension acting on both, and there's the same acceleration of both. Anyway, you've had enough time. I'm going to see what survey says here. I like C, that the tension in the rope is less than the force of gravity on B. So, why? Because, oh my God. What the hell is going on here? That looked more like 50-50 a second ago. Whoa! What are you guys doing to me here? Oh, I know, you're learning physics. I can see you learning physics. It's so exciting. Okay. I just love that. This is the power of technology. Okay, we've got 5 minutes. So, so what I wanted to do So basic idea. This is accelerating towards the right, so this is accelerating down, so that means that the net force is down on B. Net force on B. Net force on B. Sorry for my handwriting. You get me? So what I have to do is do a force diagram of B to answer this question. And it looks like this: tension and the force of gravity. So, and we want the net to be down. So I think what that means is that Fg has to be greater than the tension. You have to have more gravity pulling down than tension pulling up in order to give the net force down. Does that make sense? It's the only way it's going to work. So another way of saying that is that tension is less than F sub G. That's where I got that from. Do we have time to actually do it? Yeah, we do. Let's do it. What if you were asked, what is the acceleration of, say, mass B? Well, what we can do is we can say that for A, the x direction is what matters. So A is in the plus x direction. And for B, so this is x, I guess, it's the y direction that matters. There's a pulley in between, matters. And acceleration is down, I guess. So we could, I don't know, we could put plus y down if we wanted. Anyway, let's do a force diagram of A. It's going to be, there's going to be a normal force, there's going to be ma times g. Those are going to cancel, and you've got tension pulling it towards the right. So the acceleration is equal to the tension divided by m sub a. So that's pretty much all I need to know about A. For B, the force diagram looks like this. You've got mb times g, and you've got the tension acting up. So the acceleration is equal to, let's define plus is equal to down here. So I'm going to have mb times g minus the tension, all divided by m sub b. But these accelerations are the same because they're linked up. And so, and also the tensions are the same. So I got to be careful. If I set A equals A, I'll eliminate A and solve for tension. I don't want that. Let's set T equals T to eliminate tension. So let's solve for T and then eliminate by making eliminate T. So I'd say that T is equal to m sub A times A, and I'm going to plug that into A is equal to mbg minus ma times A divided by mb. So I can multiply both sides by mb times A is equal to mb times g minus ma times A. Gather like terms of A on one side of the equation, mb plus ma all times A is equal to mb times g. So A then is equal to mb times g divided by the total mass, ma plus mb. So it's equal to 3.5 times 9.8 divided by 3.5 plus 13.2. So I got 2.05 meters per second squared. Okay. Maybe I'll say A is equal to 2.1. That's the magnitude of the acceleration. So this one is going down, I guess. Okay. So thank you for that. Don't forget to read up on friction and consider, does friction always slow things down? We already talked about this a little bit. Static friction between your feet and the floor is what allows you to walk. And walking sometimes involves speeding up.